Thanks, Avi. So yeah, this talk is about theory of acceleration, not in the Newton sense, but in like optimization sense. And I'm going to survey actually essentially all the acceleration algorithms that I have in mind, I happen to know, and also connect them together. So first of all, what is acceleration? Let's take a simple, maybe the simplest example, which is always my favorite. Suppose we want to solve a linear system, ax equals to b. And suppose here that the matrix A is, say, even strictly positive definite. I'm using this curly larger than or equal to mean that all the eigenvalues of A are strictly larger than 0. And also define the condition number of the matrix kappa to be the lambda max. I'll say it's a symmetric matrix. Then it's lambda max over lambda min. OK, this is typically called the condition number of the matrix, or sometimes just abbreviated by kappa. So one can definitely use like Gaussian elimination or whatever algorithms to solve this linear system, but that typically requires a running time that could be large, and therefore people do care about iterative algorithms. In particular, the first algorithm that we can come up in mind is to use Taylor expansion. That is to use the following polynomial, because A inverse equals to, say, 1 over lambda max, then A over lambda max inverse, then equals to 1 over lambda max, identity minus A over lambda max. And now we see that using expansion, this is nothing but the summation of the following polynomial with respect to matrix A. And sorry? Oh, yeah. OK, so this is Taylor expansion. And suppose that we truncate this series to degree, say, degree n, and call it Pn, meaning that I just do the summation from 0 to n. Then the following famous theorem tells us how well maybe not theorem 1, but theorem. The following theorem tells us how well it approximates A inverse. In particular, if we use Pn of A, which is a polynomial on the matrix, multiplied to this vector b, and we compile it to the true inverse, the distance is going to be less than or equal to epsilon as long as maybe epsilon times b, the norm of b, say Euclidean norm if I don't clarify. Then, as long as n is larger than or equal to omega kappa times log 1 over epsilon. So basically, we need a polynomial if we use Taylor expansion. Then we need a polynomial of degree at least kappa, which is the condition number, times something that so-called linear converge, meaning logarithmic dependence on 1 over epsilon. And then we are going to have a pretty good polynomial that approximates the matrix inverse, if the matrix has a condition number here.
So that's a simple theorem.
That's a simple theorem, yeah, not hard to prove. So leave as an exercise. So then at a very high level, the whole idea of acceleration is to make this degree to be quadratically smaller, meaning that I want to construct a polynomial whose degree is only omega square root kappa times log 1 over epsilon. So this is the simplest example about what acceleration means in optimization. But before I move there, let me make some very quick comments. The first one, even if A is not PSD, say A is a symmetric matrix, but as long as, then we can always take A square. We can solve A square x equal to AB. And then A square is a strictly positive definite matrix as long as it doesn't have 0 eigenvalues. And therefore, although the condition number will be blown up by a factor, by a square factor, but this is somehow necessary. So that's the first comment I want to make. Therefore, this being positive definite is really a sign issue that it's for simplicity. And the other thing is that for this polynomial Pn in particular, if I write, say, 1 minus x Pnx, I look at this polynomial, and let me plot it. First of all, let me assume maybe for the first 30 minutes of the talk, let me assume without loss of generality that lambda max equal to 1. Then I don't really need to carry around all of the denominators. And then this polynomial, if I plot it, here is how it looks like. This is 0. This is, say, 1. It's going to be, so first of all, it equals to 1 at point 0, because this is a polynomial, and it's 1 minus 0. Therefore, it has to be here. And if I put a point to be 1 over kappa sitting here, then this polynomial is going to behave essentially like this. It's actually a monotonically non-increasing function, and it satisfies that for all of the x inside the range 1 over kappa and 1, then this polynomial is very close to epsilon as long as n is larger than kappa log 1 over epsilon.
Can you say what the complexity of solving this, if you just wanted to solve it, rather than doing it this way? Like, what is the complexity?
The naive way to solve this thing requires the matrix, takes running time dimension to the omega. And omega is the fastest matrix multiplication exponent. Currently something like 2.24 whatever. Essentially like all linear algebra computations, except the eigendecomposition, except that one, runs in time like this. Which, at least to me, it wasn't really that trivial to see, but for each problem, people have worked on how to reduce it to matrix multiplications.
You still have to use matrix multiplication.
Let's see. So here, I'm still in the. I'm going to make several remarks here. So I was trying to make this remark, but I will come back. I promise I will come back to the computational time. So the first remark here is regarding how this polynomial looks like. And if I tweak the polynomial a little bit to write it like this, then this is the property it satisfies. And essentially, this is equivalent to the theorem sitting here, actually, except that maybe I should put a kappa here. Maybe not kappa. But there's some maybe different constant sitting there. But roughly, the reason is that if we have a matrix whose eigenvalues are always between 1 over kappa and 1, then if this is true, it means that we could really kill all of the eigenvalues kind of in this range. That in particular means that identity minus APA, when, say, multiplied to a vector b, is less than or equal to epsilon times b. So therefore, this is one particular way to prove that. But of course, now we need to prove this property about the polynomial. That's one remark. The second remark is about the running time. So the running time, I claim that the running time of computing Pna times b, we can do that in time, just say n times the number of non-zero entries of the matrix A. And here, we can only do it for one vector b. If you do it for another vector b, you need 2 times this running time, unfortunately. This is not the same as matrix inverse, in which you can do that really for multiple vectors. But people really do, but you can speed it up a little bit in the sense that you can use, say, Johnson-Lindenstrauss compression to compress really this matrix polynomial into a lower dimensional thing, like epsilon log over epsilon square. And then you can use that to tackle multiple vectors. But for now, for this talk, let's only focus on solving that for one vector. So the running time is n times the number of non-zeros of the matrix A. And as I kind of forecasted a bit, that is the optimal. This is, in fact, the optimal thing we can do in the worst case is that we can get a polynomial with a degree only square root of kappa that also satisfies the same thing. And if that is true, then this running time is only square root n. Maybe I shouldn't use the letter n. I mean, n is n was kappa 1 over log 1 over epsilon. And if you change it to a new polynomial, this is what you can get.
Yeah, and it's probably you want to say for the size of the matrix.
Yeah, so say the matrix A is D by D. Okay. There, for some reason, like for the things I'm going to talk about next, people typically use N. So.
Can you explain why this polynomial is enough?
Oh, you mean? Oh, yeah. So again, that's a very good question. So, if you have a polynomial with degree n, then not necessarily you can compute the polynomial on the matrix times a vector in this running time. It depends on how the polynomial is like explicitly written, for instance. So in this Taylor expansion form, it's quite naive. We can do that in time n times n, the degree times n and z, because you just compute. You first compute b. Remember, you want to multiply this with b on the right, right? You first compute b for the 0 order term, and then you multiply this matrix on the left, taking n and z time, then times b, then add it up, then you further multiply it with
no,
this.
this was not my question. My question
Sorry.
is how is the matrix is related to the polynomial?
Yeah, so if we have a polynomial, say any polynomial p, which is a univariate polynomial, then PA is just defined to be, yeah, if this is 1 plus x squared, then this is like identity plus a squared.
Why what?
Why one inequality implies that?
You mean why this one implies that? So it's because there's an equivalent weight to this, which is if we decompose, so actually assume without lots of generality that A is in its eigenbasis, meaning that A is just, say, lambda 1 until like lambda d, then this polynomial is nothing but p lambda 1 until like p lambda d, right? And therefore, as long as we can make the eigenvalues of the matrix to kind of diminish under this polynomial, then if you put in the matrix, it's also true. Yeah, that answers your question. Let me move this up.
So you come up with any polynomial that has this property?
Exactly. So I'm going to talk about the optimal polynomial that will satisfy this now. And in particular, but to be precise, not all polynomials, because it depends on how the polynomial is explicitly written. For instance, if it's in this form, then definitely yes. But sometimes, if you write it in a very, I don't know, if say just the number, it depends on the structure, on the formula structure. Sorry?
You can always write it as a...
Oh, good question. So I'm going to come back to that very soon, but a little bit taste here is that, for instance, this polynomial here, we can expand it out as really like monomials in A, and then we only have at most the degree number of terms. But if you look at the coefficients in the front, they could grow exponentially large. Maybe in this case as well, I don't know. And when you have that issue, then you may have numerical error issue. And in many of the applications here, the matrix A may not be an explicit matrix. It could be some, say, Laplacian system solving or whatever that have some, say, also log 1 over epsilon convergence rate. Okay? Meaning that you can't solve it exactly, but almost exactly log 1 over epsilon for that, a different epsilon. But then, when you apply that matrix A to the vector B, you get some epsilon. You apply it again, you get, or maybe that's also fine, but if you multiply that with an exponentially large coefficient, the arrow blows up.
Yeah,
And
this depends on the degree and the coefficient size, the complexity of evaluating a polynomial.
in the worst case, yes. But in most of the good cases, you don't pay that. And this is something that will come next. Okay. So it's going to become clear. Yeah?
I wonder if you could use this notion of polynomials that are robust to noise.
There are, which happens to be the optimal polynomial and also happens to be the one robustly computed, so simultaneously achieved. So now I'm going to introduce something called the Chebyshev polynomial. That maybe let me say Chebyshev approximation theory, even in general. that at a very high level is to create a polynomial that pictorially looks like this. So remember, that was what it looks like. Something very nice, 1 over kappa and 1. And here is another polynomial that could be obtained looking like, still like dropping like this, but starts to oscillate a bit. Say I still want 1 over kappa and 1, but this polynomial, remember, has a degree, omega kappa log 1 over epsilon. But this one will have a degree, as we will see. That's only square root kappa log 1 over epsilon. So to construct this polynomial, there's actually a faster track. That is to directly use the so-called Chebyshev polynomial of the first kind. Chebyshev poly of first kind, meaning that I define, define t0x to be, I think 1 or 0, 1, yes. T1x to be 1, to be x, then tnx in general to be 2x, then tn minus 1x, then minus tn minus 2x. So this is known as the Chebyshev polynomial of the first kind. And this polynomial, if you look at it and plot it, it looks like the following. So between minus 1 and 1, it's going to oscillate, either even or odd function, I forgot. But to the next of, say, minus 1, it's going to grow exponentially large. And this polynomial in particular, if you scale it, you basically define, say, this point to be 0 and this to be 1 over kappa, then that gives you exactly that. And this polynomial has degree. It satisfies this.
The bound in Chebyshev from the y-axis is also 1. Right? This is
Yeah. I mean, you scale it both in the x sense and in the y sense.
beforehand, the way you define the polynomial between minus 1 and 1 is also bounded.
It's bounded by 1 in particular, and therefore you need to scale it also on the y side to make it like that. Yes. So this could be something like exponentially large, maybe e to the 1 over kappa. I forgot. Yeah, let me not write it.
I wonder, is it dependency on epsilon type?
In terms of epsilon? Yeah, so actually both the dependency on kappa and epsilon are tight. So this polynomial satisfies this polynomial, say maybe qn. This qn is less than or equal to epsilon for every, after scaling, then it satisfies this for all, like, say, x between 1 over kappa and 1. Maybe say, let's do a claim. As long as n is larger than or equal to omega square root kappa log 1 over epsilon. And I think it is known that both parameters are tight. Yes. And of course, I will also come back to how to compute this polynomial, but let me state actually a more general theorem about the Chebyshev approximation, which is the following. So suppose I want to compute some vector S, say big N, that is a summation of Chebyshev polynomials applied on some matrix, say A, then times some vector, ck. Suppose I want to compute this like polynomial of, not polynomial, this like linear combination of the Chebyshev polynomials. Okay. First of all, why do I care why do I care about it? On one hand, this turns out to be a special case. And on the other hand, more importantly, actually there is a general approximation theorem. Let me maybe put it here for now. That says the following. Essentially, for any function, analytical function that's analytic on some disk, then if you do it appropriately, you can use both Taylor expansion or use Chebyshev expansion, and the Chebyshev expansion will be quadratically fast, will have a quadratically smaller degree. So that's kind of the high-level idea, but it requires a bit notations to write down. Let me write it here. Definition. So for every rho that's larger than 0, define epsilon rho to be the so-called Bornstein ellipse. To be the unique ellipse that looks like this. Say this is 0, this is -1, this is +1. And then the ellipse is the one so that this point is roughly up to constant. It's roughly 1 plus rho square, and this part is roughly rho. And this is -1 minus rho square, and this is, this is like this comma 0, this is this comma 0, and this is 0 comma rho, this is like 0 comma minus rho. So this is up to some constants, like that's maybe sitting in front of the rho square, maybe 2 or whatever, but whichever that makes it an ellipse, okay? Then this is the so-called rho-Bornstein ellipse. Now the theorem of Chebyshev approximation looks like the following. If we have a function, say fz, that's analytic on this ellipse. Oh, sorry. Why did I use p? Say rho. Yes.
Can you write bigger?
Oh, yeah, sure.
Just for the comma.
OK. Yes, I will try. So suppose we have a function that's analytic on this ellipse and bounded on this ellipse. Then if we define a polynomial to be the following, let me see how to describe it. So define some polynomial, maybe let me overload the notation. So I still use Pn to be the summation of Chebyshev polynomial to degree n times ck, where ck is a constant here, and this, maybe say ak, not to be confused with there. So ak, where ak, there are two ways to define it. One is to use interpolation, and the other one is to use the orthogonal basis property of the Chebyshev things. But I would just write maybe one of them, indicator function of is this 0? If it's 0, it's 1. If it's 0, then this is 1. Otherwise, it's 2. It's a typical normalization thing. And here, each xj is the so-called Chebyshev point. That's cosine like j plus 0.5 times pi n plus 1. So you don't need to remember this, but the punchline is that if you define some so-called Chebyshev points that's between -1 and 1, now you interpolate the function f on those points. And this is essentially just the typical interpolation, but typically we do interpolation with maybe other bases, but this turns out to be the best basis that interpolates the function in the best manner. And if you do the interpolation, compute the constants, then you put them there, it's a polynomial. And this polynomial satisfies that the function fx minus pnx is less than or equal to some 4m divided by some rho plus like, just think about it being rho, it doesn't matter. Then 1 plus rho plus like square root 2 rho plus rho square to the negative n. So this is what the Chebyshev approximation theorem tells us. And let's now do a simple exercise. Actually, maybe one exercise for now. That is, suppose the function I want to compute, the fz, is z inverse. OK? Now, this function is definitely not analytic like on the real axis to the left of 0, but we can always move it. We can move it to be whatever the constant that makes sense, so that so that Z inverse, let's see. So Z inverse originally has a singular point that's here, like this. And now we move it to the left by, remember, we need to move things to -1 and 1 in order to match the format of the theorem. And then we basically put the Z inverse to be essentially this. We put it here, and now the singular point is somewhere like, this is essentially -1 minus maybe big O, a constant times 1 over kappa. So this is, now the singular point becomes like -1 minus 1 over kappa, essentially. If suppose we want to do the inversion, suppose we want this inversion to be correct for, say, less than epsilon for every Z that is, say, larger than 1 over kappa. Suppose we,
So this,
yeah,
we're
actually.
supposed to think of Z as standing for matrix A. We will later apply.
Yeah. So feel free to think about this Z being like whatever the matrix A we wanted to do, and suppose that we only care about the eigenvalues or even the value of the variable at this point between 1 over kappa and 1. Then we can shift the function a little bit so that 1 over kappa becomes -1, and the 0 becomes essentially -1 over -1 over kappa, and the 1 remains to be 1. It's like a linear transformation. And if you do it that way, you can define like the ellipse sitting here. As long as the ellipse does not touch the singular point, you plug it in, you get a polynomial. By the way, it does not have a simple form like just using one of the Tn's, but it still has the same approximation property. OK, that's a simple exercise. And we're going to do another exercise a bit later of the same theorem. OK.
The point is because the degree is smaller, you need fewer interpolation points than you need in the, if you use the monomial basis.
Yes. So that's the point. So in some sense, the Chebyshev approximation is not to do Taylor expansion, but to do the also Taylor expansion, but in the complex plane.
So you should say these are orthogonal polynomials.
Yes. So these are orthogonal polynomials under this multiplication. So, I mean, yes. But that's not, that won't be important. So let me just focus on this form now. And let's worry about how to compute it. In particular, if we have error and error propagates, then how can we compute this like kind of reasonably well? So it turns out that there is the following way. So one can definitely compute each tk, for instance, using a recursion that requires like already k iterations, and then you multiply on top of ck. But this way, the polynomial is not going to be like numerically stably computed, meaning that error will propagate and blow up. And in fact, there was when like Daniel Spielman and Shanghua Tian designed the Laplacian system solvers using like preconditioning, blah, blah, blah. And they have to compute Chebyshev polynomial, I think of this kind, just one of them. And then they don't know how to do the numerical stability analysis, and therefore they really have to blow the error up exponentially. But fortunately, in their case, the degree is only logarithmic, and therefore they pay some, or polylogarithmic, they pay some polylog factors in the running time. That's why their original paper has a lot of log factors. But now, let me propose a way to be numerical stable. And this actually showed up in a paper of me and Yuan Zhi for some other purposes, and we couldn't find out the theorem, and we proved it ourselves. That is, first of all, there is the following specific way to compute it, sometimes known as like back propagation. Backprop. This is not new. This is not by us. It says that if we compute first, in a backward manner, a different sequence of b, and we set bn plus 1 to be 0, and bn to be cn. And ever since, we do the following recursion, say br equals to 2 times matrix A, then B R plus 1 minus BR plus 2, say plus CR, then it satisfies that Sn equals to B0 minus M times B1. Which just happens to be a backward way of computing this like Chebyshev interpolation or something. Yes?
M.
Oh, sorry, M is A, yeah. And the way to prove it is basically to rely on the recursive formula of the TK. It satisfies that, and therefore, if you massage it a little bit, this is what you can get.
And the doubling is the doubling 0 every time?
Yes, the 2 sits here, it doubles. And this is why I said, like, if you directly compute a Chebyshev polynomial, the error really blows up. You see like a factor of 2 here, also a factor of 2 here, then how to deal with it. So here is the kind of idea that we also learned from the numerical analysis community, which is if we compute this Sn using this kind of recursive formula, and suppose in every iteration we make a mistake, and the mistake is a vector eta, presumably like say the norm of eta is very small, say that, actually no, I need to define it multiplicatively to be precise. Let me think, how can I do it? But for now, okay, suppose I have some error vector eta added here. Now if you look at it, what are we computing? We're computing a new vector that's not the same as Sn, but it's the same as I do this. Basically, it's a change of basis in the sense that now the error we incur in the recursive procedure becomes the coefficient of the original polynomial. And because of that, it actually gives us an effective way of bounding how the error propagates. So instead of proving this, I would directly write down a theorem about how the error propagates. That is okay. So theorem. Suppose we have a procedure, say script A, that computes every vector, say AV, in a way that it's close to X, but up to an error, multiplicative error, epsilon. Suppose we have a procedure, script A, that approximately computes the matrix vector product. V, yes. It approximately computes the matrix vector product. Not exactly, but up to a multiplicative error, epsilon. By the way, it has to be multiplicative because otherwise you scale V up, then it becomes a useless statement, right? Suppose we have this. Then suppose we just replace this with like 2 times the script A times whatever vector sitting here. You do this. Now you have error per iteration, but the final error will look like we are computing some, say, Sn prime, that's again a vector. Its distance to Sn, Euclidean norm again, is bounded by epsilon times polynomial of, it's a polyfactor time of n, and the polyfactor on, suppose all the ck are bounded by some big C, then it's bounded by a polynomial of n and c.
Where is you replace this script A? Just because?
Yeah, just because we don't have exact matrix vector multiplication routines. And then you incur some multiplicative error per iteration, but the final error would be this. And by the way, the poly is not really very big. Maybe something like n square. I didn't try to improve it. But the punchline is that it's not exponentially large. It's only polynomially large. Meaning that if eventually we want an epsilon, if we want an epsilon prime error, then it suffices to pick this epsilon to be like epsilon prime over over polynomial of n. And now it means that you only need to solve this to an error like epsilon prime over, say, n squared, ignoring maybe the factor c. And because most of the routines that will solve this up to a log dependence on this arrow, and then it becomes only a log factor. So not very big. OK?
What is the magic? Where did the factor 2 for the exponential blow-up disappear?
Oh, the magic is really because so in every iteration, suppose we have some arrow. We put the arrow here, and then we kind of put it into the original polynomial, and then we use the property of the polynomial, which is the polynomial between, say, -1 and 1 is bounded. We just say that it didn't blow up the original vector by much. So the magic, another way to think about the magic is really that if we bound it naively, we are really losing information. We're forgetting the fact that it's a polynomial. It's the Chebyshev polynomial. That has some interpolation property. And therefore, if we kind of write the arrow like in a different basis, in the original basis, it becomes bounded.
So what is the property? Where do you use the factor 2? 2 goes into the C. Where does this 2 go to?
So so first of all,
one we wouldn't have to worry at all, right?
Even if actually there's 1, then this minus doesn't really cancel two arrows. If you have arrow 1, arrow 2, it becomes plus. So I mean, the factor 2 and the fact that we have a addition of 2 vectors here really makes the arrow like not easily like bounded.
I'm asking
yeah.
for which. So you want this difference between S and prime and Sn for this sequence,
So yeah.
Linear. Oh, I see. So you're just saying any linear transformation, any linear combination.
Yeah, for any right.
Is has this property.
Yeah. So actually, let me state it maybe more precisely. For every polynomials of Chebyshev, actually every linear combinations of the Chebyshev polynomials, but in the matrix form, and suppose that the eigenvalues of A are between, say, -1 and 1, it's up to shifting. So whenever I'm writing something like this, I assume that the user has already shifted things, to the -1 and +1. Then assuming that all the eigenvalues of A are between this range, then consider 2 procedures. Procedure 1 computed exactly. Procedure 2 computed using the backpropagation, but every iteration you replace it with an approximate matrix vector multiplication routine. Then this is the final arrow guarantee. Yeah.
And then it will take again the degree times the number of non-zeros.
Yes, then the running time, if you look at here, I mean, if this is an explicit matrix, then computing matrix vector multiplication is only n and z, number of non-zeros of the matrix, then you only need to do that n iterations if the total degree is n. OK, did that answer your question, Abhishek? Now essentially for every linear combination of the Chebyshev polynomials, as long as the coefficients are bounded, then the final thing is also bounded. OK. To our surprise, it was not known until like our writing, but it's a simple thing, not hard to prove. So let me see what's next. So that's the Chebyshev polynomial thing, and in particular, it helps us to compute the, say, matrix inverse in a time that's square root this.
So this is just showing that you have some stability in the algebra.
Yes, yes. And now I'm going to come to something.
If I were to do the same thing in the
conjugate
Taylor series, it doesn't work? Or?
Oh, so for Taylor series, I didn't prove it, but I think it will work. So Taylor series will also have some similar property to this. Although not naively seen from here, maybe. Or maybe here is already fine, because we're just looking into the basis of this polynomial, this like thing, whole thing to the kth power, but because the spectrum of all the eigenvalues of this matrix, identity minus whatever, is bounded, then it doesn't blow up. So yeah, it's actually a simple thing to prove for Taylor series, but in general, it requires some efforts. So now let me mention something that's very related to the Chebyshev approximation theory, which is the conjugate gradient method. And many people know that conjugate gradient is not stable. Okay, and let me now say what it is. So actually, instead of exactly defining conjugate gradient, can everyone see it here? Maybe not. Maybe. Let's see. So maybe from here.
A little bigger for me.
Oh, yes, I will try. Yeah, maybe let me erase the part above. Yeah. So actually, in addition to the Chebyshev approximation, there is something else. And I promise this is the last thing I will tell you before I draw like an overall picture, like summarizing all the methods about things I have said, things I will say like maybe later. But this is the last thing before I draw that picture. So conjugate gradient. So suppose, again, that we're trying to solve this linear system, like with A being like a strictly positive definite, and with condition number kappa. Now the idea of conjugate gradient, I'm not going to define it today. So people even write surveys about conjugate gradient without acknowledging pain, meaning that it's a bit painful to even write down the algorithm. But instead of doing that, let me just claim intuitively what it is doing. So consider the following matrix of column vectors B, AB, A square B, until like something like A, say big N B. So this is the matrix with n plus 1 column vectors, each vector in the original dimension of the problem. Then the idea of conjugate gradient is to do Gram-Schmidt, to turn this column matrix into an orthogonal matrix, say V. And then conjugate gradient is a method that will make sure that in n iterations, it's going to find a vector xn. And it satisfies that the arrow term, remember we want this to be 0, right? And the arrow term, if up to iteration n, is going to be orthogonal to this, say, Vn, which in particular means that it's orthogonal to the original, original matrix. But this Vn is column orthogonal. And more precisely, it's going to make sure that.
This is again like truncating the Taylor series. So what you want is
not the. I'm going to explain that. So it's not exactly that. But first of all, let's see the guarantee. So the guarantee is that, more precisely, this arrow is less than or equal to, less than or equal to maybe B, the norm of B, times the minimal polynomial of degree n, then the polynomial applied to matrix A, let's see, times B minus A inverse B. Let's see, so no, what do I mean? Maybe I should do this. Polynomials, and maybe the max. Yeah, I should do a min max. The max over all the x. Maybe no, let me not do the max. I'll just do Pn A B minus A inverse B. Yeah, if I do that, then I don't have the multiplication. So it means that the arrow of this thing is going to be at most whatever polynomial take up to degree n. I put the polynomial here, multiply it on the vector B, and I compare that to the true thing I want to compute, and then my error is going to be as good as that polynomial. The reason, okay, so let's see. Multiply it with, sorry, with what? Yeah, yeah. Maybe there is a factor kappa or something sitting here because, yeah, maybe let's see. Maybe let me do this. Then it makes sense. I compute xn minus a inverse b. Then I think it makes sense, right? Yeah, it's a scaling issue. So let's see. So this orthogonality thing actually implies this inequality. Because if my arrow thing is already orthogonal to all the vectors sitting here, then in particular, I can choose any polynomial, which is a linear combination of the columns sitting here. And my arrow term is going to be orthogonal to that quantity, to that vector. So this is not a formal proof, but intuitively, this is going to help you to ensure that for that particular polynomial you choose, then you have the property that is your final arrow is less than or equal to as if you're using that polynomial.
So what exactly are you doing to this matrix of column vectors? You're orthogonalizing the rows, the columns?
Right. So maybe say for this analysis purpose, I don't need to do orthogonalization. I just construct, say, I just construct this and call it, say, Vn. And then as long as I claim, as long as the algorithm can make sure that this is orthogonal to the space, then this is true, up to some scaling. Yes.
And where do you get that with the axn?
Yes, then that comes from the conjugate gradient. So the conjugate gradient method, so two claims. First, the conjugate gradient method is going to produce a vector xn satisfying this orthogonality. Claim 1. Claim 2, if the orthogonality is ensured, then we have this approximation guarantee. That is, the approximation error is at most the best degree n polynomial you pick, then I compute the approximation.
What happens to this if B lies in some small eigenspace?
Then this is 0.
Oh, once you completed the entire eigenspace.
That is right. You exactly get the solution. So yes, a few remarks I'm going to make. Let me directly go to that. In particular, if, say, I choose this n to be the dimension of the problem, then I get the entire space. And therefore, this minimization is 0. That means that using like n iterations, I'm vague here because I haven't defined what conjugate gradient is. So conjugate gradient is a method that requires this n iterations to find such a vector. And each iteration, again, something like a matrix vector multiplication, something similar to the polynomial computations. So you should think about this n to be the same, in some sense, the same n sitting here. Okay. Then in n iterations, conjugate gradient is going to produce a vector. And if this big N is larger than the dimension of a problem, then the error is 0. In theory, the approximation error is 0.
So you want to say that xn is the projection of A inverse B on the subspace?
Yes, I should maybe.
It's not completely clear if the condition AXN minus B is orthogonal to.
Right, then it could be very large, like up to a scaling. Yeah, I agree. But so maybe I should. Is there any symbol for projection? Maybe. Yes. Say E equals to the B, then projected to VV transpose. I mean, if V is orthonormal already, so let's orthogonalize V and then define it to be either left multiply or right multiply, whichever that makes sense. I mean, projected to the orthogonal space. So let me not go into the, let me not define it precisely and say it's orthogonal to the space. Okay?
Will you tell us how?
Roughly, very roughly, yes. So that's the second thing, that is how conjugate gradient works. So in theory, you can always do really like a naive Gram-Schmidt. That is, you now have a vector, orthonormal, a second vector projected, the third vector projected to the previous two columns, and so on and so forth. In that way, the running time will be n square times the,
What will be the final vector?
sorry?
What will be the final?
Oh, so once you have like say n orthogonal vectors, you just do a projection. You start from vector b, then you project it first to. Good question. So actually, in some sense, you project it not directly here. Otherwise, in the first iteration, you're done. But in some sense, you project it column by column. Yes, you do the inner product, you subtract it. So this is like going to be very vague.
So I'm wondering how this compares to this other algorithm.
I will do a comparison very soon.
I mean, it seems like if you would choose the polynomial independent of just as a function of a, then if you would choose the coefficients of the polynomial not to depend on b.
Exactly.
Then,
yes, then
get
it
the
matches.
same thing.
Exactly. I'm going to come to that. You're a step faster then. Okay. So, but before that, let me roughly say like how conjugate gradient works and how roughly this vector xn is computed. The naive way is to do like a true Gram-Schmidt orthogonalization and then project the whatever the thing into this subspace, in some sense. And then there's a faster way, which is to do the following. So suppose one has like an already orthogonalized column matrix, column orthonormal matrix, like of the previous iteration. And now suppose you want to compute the new matrix. And then the idea of conjugate gradient is to find a vector, some special vector from the space, so that the span of this column matrix equals to the span of Vn minus 1 and A times V. Meaning that instead of like adding a vector like this, which might be a bit complicated to compute, let's find somehow a magical vector V. In particular, if the original matrix is not orthonormal yet, then I can pick, say, A to the n minus 1 times B and multiply it on the left-hand side by A, then it becomes the same in the column span as this matrix, right? But because of the orthogonalization, one has to do it more carefully how to choose the vector V so that once you append it, it's in the same orthogonal, it's in the same span as V as the thing we want to compute. But moreover, the algorithm is going to ensure that AV is already orthogonal to Vn minus 2. Meaning that if we want to do a Gram-Schmidt, we don't need to do that from the first column from the beginning anymore. It's going to be very efficient, and we only need to orthogonalize it with respect to the previous column. Maybe the previous two, I forgot. Something like that. Yeah. And that was the kind of rough idea of conjugate gradient. That is to compute the orthonormal basis of this matrix in a faster manner, meaning that only requiring order n times of the matrix vector multiplication. And then once you have that like column orthonormal matrix, you can do the projection of the thing easily. That's the very rough high-level idea of conjugate gradient.
So is there a time analysis of this?
Yes, that will come. So far, I only said this. I haven't connected it to the Chebyshev polynomial, which David already mentioned the solution actually. That is in particular, if I suppose this matrix A is whatever I want to invert, this original thing, and suppose I pick this polynomial just to be the Chebyshev polynomial, then it gives the same guarantee as here. Meaning that I only need this number of iterations, and I can compute the inversion to an epsilon error. Okay? So, but you can see like that is a worst case analysis, meaning that it doesn't really need the information of this vector B. It doesn't need the information of this matrix A. And in particular, as Adam mentioned, if say I draw the eigenvalues of the matrix A, say maybe it's larger than 0, between 0 and 1, suppose I draw the eigenvalues of matrix A. If they sit kind of quite arbitrarily, then maybe I have no idea what to do. The best polynomial I can do is to use the Chebyshev polynomial to kind of cancel them out. But maybe, say, there are a lot of multiplicities, meaning that, say, there are maybe at most, say, k distinct eigenvalues of the matrix A. Then we can do interpolation. There always exists a degree k polynomial that kind of that goes through all of those, like, say, k points. And if you use that one, you put it there, you get 0. So you get an exact solution. So in principle, this performance really depends on the eigendistribution of the matrix A. And some people do prove things like if the eigenvalues are clustered to some range, then how large is the number of iterations? It depends on quantities. But in general, in the most general way, if you only want to write it in terms of the condition number kappa, then that's the best you can do. The best you can do is to put in the Chebyshev polynomial. OK? So does this answer some of those questions?
Yeah, but so what? It would be nice to have what's the best general bound of any method to compute a solution to a system like this. A equal B. Let's say A is a positive definite, and it's in terms of kappa, the dimension, and epsilon. We want to approximate it to epsilon. What's the best running time we know?
The best is definitely this one, and
So the running time here is square root kappa log 1 over epsilon times the what times the number of non-zeros.
So if you are not, so that's a good question. I'm going to come to it in the next half of the talk. That is regarding, for instance, for solving linear system, what's the best running time? If we only care about kappa, the dimension, then epsilon, then what's the running time? So at a high level, if we do not use any special property of about the matrix, meaning that we only do matrix vector multiplication as a black box, then I think this is the optimal thing one can do. But I need to check. I don't exactly remember. But if
matrix vector multiplication, where the matrix is the original matrix or are some other matrix?
Is the original matrix, yes.
So
or maybe plus a bit identity.
Okay.
But that's fine, yeah.
That's,
Yeah, okay.
But multiplication you do only with the matrix, right?
Yes, yes, yes.
I see. So if you have just a black box to multiply your matrix with any vector given,
Yes. Then you can do that.
the number of multiplications is just this,
Exactly.
and that's optimal.
And that's optimal. Yes. To get to this question a little deeper, a little like forecast of what I'm going to talk about next is that, for instance, sometimes we are allowed to multiply it not with the entire matrix A, but with, say, a random row of A, which is a lot faster. A dimension, say dimension is d, then d times faster to compute. Then we can do it in a much faster running time. And that's known as coordinate descent. It's going to come later. But for now, before I draw the general picture and call it a break, let me mention some important things. That is about the numerical stability again. Yes, it's unstable. So Avi just mentioned like a black box kind of model. And suppose the black box model is not exact, meaning that I have a black box that can help me to compute the matrix vector multiplication to an arrow like this. Then there is no known guarantee for conjugate gradient. And in particular, it performs really poor, and the arrow blows up crazily. One of the issues is that if you do this kind of analysis, then the new vector is not necessarily completely orthogonal to the previous, say, n-2 columns. And then what do? The best thing you can do, to my mind, is to orthogonalize it to all the previous columns. But if you do it that way, you're not really accelerating. You're at least then the number of computation, the number of oracle cores becomes n squared, no longer n. Okay.
Can you say when is conjugate gradient useful compared to a simple Chebyshev?
So very good question. So conjugate gradient, if you do it, say, to 20 iterations, it's very useful in practice, yes.
Okay. I guess not necessarily in practice.
Oh, in theory, so to mention just one example that I'm very familiar with, that is the Laplacian system solving things of Spielman and Tan, and then the follow-up like Richard Penn and a lot of like preconditioning, blah, blah, blah. So all of those things, in principle, can be implemented using conjugate gradient.
But couldn't you do it in a simpler way with the Chebyshev?
Yes, and but they couldn't analyze the arrow blow up things, and therefore they use all of them in the end used the Chebyshev iterative method, which is the Chebyshev polynomial thing. Yes. So maybe the kind of the high level, the rough answer to this question is that if you really want to prove a theory paper, maybe not very useful. Yes. In the end, one has to more or less use the Chebyshev polynomial thing. But in practice, if it's like for 20 iterations, it works. But more than 20, maybe not. Something like that, yes. So now let me draw a quick picture before we call it a break. That is as follows. This is going to be big.
Is there a way of stabilizing it? Is that what you're going to tell us or not?
So you mean for conjugate gradient?
Yeah.
So there are several like ways to try to stabilize it, which I'm not a very expert of, and to the best of my knowledge, they don't have very good guarantee either. So only this Chebyshev method has a guarantee, and this, like to the surprise of my mind, like it wasn't even known before until like a few months ago we proved it. So kind of surprising. But the punchline is that many of the numerical analysis people, they worked on or at least to this like Chebyshev polynomial people, they care about not with respect to matrices, but with respect to maybe say scalars. And then they try to analyze the error over there, which is a bit different from the error like incurred from the matrix vector multiplication, which is what we kind of care the most in our community. So it's a bit different over there. But for conjugate gradient, I don't have any knowledge about any stable like variant of that. So let me draw a picture maybe here.
It's also be clear what
Yeah?
the theorem statement should be, right? I mean, if you
Could you repeat the theorem statement for what?
What would be, like if you wanted to stabilize conjugate gradient, it's not clear what's the theorem statement that you would want to do.
Right, like there exists a method that's epsilon close to conjugate gradient that does whatever good. Yeah, it's not clear. You need definitely a different method. And then ideally, the method had better to behave more like this as compared to the worst case analysis of the Chebyshev method. The Chebyshev method is oblivious to the eigendistribution of the matrix. But this one is kind of trying to really match the best polynomial, and then it's kind of tricky. There are a lot of like open questions here, which once I plot the picture, it will become clear. So let me draw like two circles here. So the simplest example, or the canonical example, ax equals to b, sits here, and the conjugate gradient method sits here. It solves ax equals to b, this problem. But the whole idea of Chebyshev approximation actually sits in a bigger circle, meaning that suppose I want to compute some e to the matrix A times a vector. This is no longer like A inverse times a vector, but say e to the A times a vector. And this matrix A, suppose like all the eigenvalues are less than or equal to 0, but larger than or equal to something like minus lambda. So meaning all the eigenvalues of A are between minus lambda and 0. Then one can also use the Chebyshev approximation theory. Maybe I won't do it today. One can also use that to construct a polynomial on A, satisfying that when you compute the polynomial, multiply it on B, and compare the distance, this is going to be epsilon as long as n is larger than or equal to square root lambda log 1 over epsilon. Maybe assuming like lambda is larger than 1, say. Then you can also do it in an accelerated way, meaning that with a square root dependency on lambda. And in contrast, if you do Taylor expansion, it's going to be lambda. This is the Taylor expansion. To sum up,
Of e to the a.
sorry?
Of e to the a.
of computing e to the a times a vector b. To sum up, the Chebyshev approximation theory can solve some problems that are more complicated than linear system solving. But the conjugate gradient method, it has some practical generalizations here, but there's no theorem that one can prove to the best of my knowledge. And conjugate gradient is a bit more restricted. And in the second half of the talk, I'm going to talk about convex optimization that sits kind of in this bulb. That is essentially to minimize a function fx. One can also talk about the non-accelerated running time and the accelerated running time. And the algorithms here, in particular, can also solve things here. But they can be much, much more general than this, just similar to the thing sitting here. But so far, to the best of my knowledge, this problem doesn't fit here. OK. And one more thing to comment before, yes, that is, Avi just mentioned what's the best running time we can solve this. And I said, for instance, we can compute a random row of the matrix and times a vector that's a factor d times faster to compute. Then one can talk about what is the running time. This becomes the so-called coordinate descent method kind of running time. It's going to be it's going to be definitely faster than the full gradient-based first-order methods, which more or less correspond to the conjugate gradient or Chebyshev approximation things. So kind of another way to say it is that once we start to have convex optimization, we have more tools, something like coordinate descent or stochastic descent, stochastic gradient descent. We can have more advanced optimization tools to help us to even get faster running time, say, for the linear system solving. But so far, not for this. So these are, in the very end, I'm going to come back to this picture again to raise some open questions. But the second half of the talk will be mostly about here. Yes? Any other question?
Yeah, so this is, when one tries to diagonalize matrices, the Langsos method, which is very much in this spirit, right?
The Langsos method is in the same spirit as this. So right, there's at least another problem, say computing the eigenvector, say the top eigenvector of a matrix. Yeah. So that problem, I have to say that it, in some sense, lies outside, a bit outside. For instance, thinking about getting, say, the top k eigenvectors. One can still use Langsos method. It's kind of in the spirit of this. But in the end, that one can use convex optimization to solve it much, much faster than even Langsos. And that is also some of my work, but I probably don't have time to.
The top one, I can imagine, is better, but the lowest one you can also do similarly?
You mean this one?
Yeah.
Oh, the lowest. Oh, yeah, the lowest, yes. But say the top 100. Yeah. So one can use Langsos, and the Langsos looks exactly like conjugate gradient, and it's not stable. That's right. It's not stable. And one can do something like Chebyshev, but one can do something, it's similar. Like one can do the Langsos, one can do Chebyshev, and one can also do convex optimization. But the punchline is that whenever a problem fits into the convex optimization ball, one should not use the classical tools, and they're going to give you slower running times. Yes. But I probably don't really have time to talk about that today. Yeah. Mm-hmm. Okay. Thanks. So let's have a break. In the first an hour, I waved my hand and talked about Taylor expansion. That's essentially think about ax equals to b as the canonical example in this talk. Then solving that is equivalent to finding a polynomial like Taylor expansion polynomial to approximate something like that. And Chebyshev is sharper, faster, and oscillates a bit. Then conjugate gradient is finding some orthogonal basis and so on and so forth. So that's a quick recap. And in this second half of the talk, I'm going to switch the gears to talk about convex optimization. And then some of the running times here will be connected to the things I talked about in the first half. And in particular, the whole theory of acceleration, or even the name of acceleration, was first given to the convex optimization world and then got related to the things over there. So consider the problem of minimizing some function fx. And we can feel free to, for simplicity, to think about this function being maybe, say, 1/2 x transpose ax minus b transpose x. And if this is the convex function we are minimizing with respect to a positive definite function matrix A, then we are solving ax equals to b. Okay? That's why I said, ax equals to b is a special case of convex optimization. So this is the example we should think about. We should think in our mind.
You're taking the derivative.
Oh, yeah, just take a derivative. But of course, there's a deeper issue that is, if I get an epsilon approximate minimizer for this function, how does that translate to an epsilon approximation to that? But if things are logarithmic, like log 1 over epsilon, then it's not a big deal. Yes. So now a few notations. So of course, the Hessian of the matrix at a point. And because I'm interested in convex functions, the Hessian is PSD. And say that the function is L smooth if all the eigenvalues of the Hessian are less than or equal to L.
Now you're looking at high-dimensional.
Oh, yeah. Oh, right.
Where x is in our
Good question. Yes. So this is a function f is like from, say, d-dimensional space to Rn, to R. OK, so it's not the x I cared about earlier. OK. So this function, its Hessian is a d by d matrix. And I say that the function is L smooth if all the eigenvalues are bounded by upper bounded by L. And I say that the function is strongly convex if all the eigen, meaning sigma, say strongly convex. If all the eigenvalues are at least sigma. Okay? In particular, if f, we should always think about the, this fx equals to the 1/2 x transpose ax minus bx as a canonical example. And in this example in particular, we know that then we know the Hessian equals to a. And therefore, the L over sigma is essentially the kappa that I talked about in the first half of the talk. Okay? So, but more generally, like these are the notations that people use in convex optimization. So, under such a model, a model of the class of the function, the convex functions, then people talk about first-order methods. Meaning that essentially I only make queries to the function and compute the gradient. Or maybe pictorially, it means that, say, I'm the algorithm. I keep making queries at, say, point xk, and then the function, the oracle, whoever that tells me about the gradient at the function at the point, say, xk, and maybe also the function value, maybe not. It doesn't really matter in this talk. But most importantly, the oracle tells me about the gradient of the function at any point xk that I query like in iteration k. So this corresponds to the oracle model of the, say, the first half of the talk, because if this is the function, then this is nothing but axk minus b. It's just the matrix vector multiplication. So first order things are usually like much easier to compute than many other things of the other properties of the function. So then the whole point of first order method is to construct an algorithm that makes as few queries as possible to the oracle in order to find a point in the very end, so maybe say xt, so that its distance to the exact minimizer is, say, at most epsilon. In such a case, we say that it's an epsilon approximate solution to the convex optimization problem.
So if I use the second order method,
Okay.
am I going to get a lot?
So in this talk,
Right?
I'm not going to touch almost anything about second order method, but it's a very good question. So at the very beginning, I thought the following. That is, second order methods typically requires you to compute, say, the Hessian of the function maybe sometimes like regularized a little bit, and then you do inverse, something like Newton's method or regularized Newton's. Yes, it converges much faster, but the issue is that computing, now it becomes like a new matrix inverse that we want to, a new matrix we want to invert. And in particular, if it's the function, if this Hessian is A, then it's essentially the original problem, but maybe with a better condition number for a different lambda. So actually, this past a month, we submitted a paper to Stock making actually second order method also run very fast. The essential idea is that, but second order method for non-convex optimization. Over there, the idea is that for a more like complicated problem, then if you compute the Hessian, look, it's nothing but a matrix inverse, right? A matrix inverse, you can use some either conjugate gradient, which will be slow, but if you use some convex optimization techniques to solve it, it could actually be fast. And therefore, sometimes second order methods can also run even maybe faster than first order method, but I won't touch it today. It's kind of a more complicated issue. So yeah, let's only focus on first order methods. Yeah. How hard could it be? Yes.
No. I'm just wondering whether the following fact for my sort of arithmetic complexity is known. So when people compute, you will need the gradient is all first partial derivatives of a function.
That's right.
Maybe it's some polynomial of high degree.
Mm-hmm.
How do they compute it?
First of all, there are definitely functions that whose gradients don't maybe even exist, say not even differentiable.
No,
or
it's a polynomial.
A polynomial.
Yeah. So how do if I give you a polynomial of degree d, right?
Okay. But how is it written? Say.
Yeah, it's a circuit. So let's
it's a circuit.
Given by a circuit of size s. So just pluses and times at the end. Yeah. So if this is
So if it's actually a circuit, then one can use the derivative rule of composite functions in some sense. That is, whenever I have like, say, f of g. So the quick answer is that computing that if you have a circuit of size, say, d, or the size s, okay, then in linear time with respect to the size of the circuit, you can compute it if all the gates of the circuit are differentiable, right?
So how do you call it? I mean, yeah, we call it arithmetic complexity. We call it the Bauer-Straße.
Interesting. So
it's a very old paper, and it works. Yeah, in general.
I see.
Yeah, the gates are, let's say, they are just plus and times. So.
Right. Then definitely
so
yes.
This is, I guess, was discovered as well. This is.
And by the way, that even works for second order.
I think it's
more general.
Yeah, when it's differentiable, it's more general. It's probably the same proof because that's all you use.
Exactly.
That's all you use in the.
Right.
So the name that goes with it's really interesting.
So I don't. So actually, this thing got recently popularized in the machine learning community because even the second order thing can be computed in the same running time in the following sense. If you have a function f that's represented in an arithmetic circuit of size s and say all the gates are even twice differentiable, then computing this thing, the Hessian multiplied down to a vector, also takes a running time that's linear in terms of the size of the circuit.
Yeah, that's like,
yeah.
Okay, it's not so yeah, if you told me the Hessian could be linear, that's impossible. But
Right.
By a vector,
Exactly.
This is something that should have.
It's just to apply the theorem twice. Yeah. I'm not saying anything fancy.
No,
I'm just.
No. It's
yeah.
it's not fancy. It's far from obvious at all. Forget the second line, the first line.
Oh.
I give you an arithmetic circuit of size s
Mm-hmm.
for a polynomial, multivariate polynomial.
Mm-hmm.
Compute the gradient. I think the fact that it can be done in linear size.
Right.
By another
Yeah, it's
circuit of
not.
size 5 times s. To me, is one of the magics of
I agree.
magical results. So
I agree.
know when it was discovered in the arithmetic complexity.
I see.
Community. I wish I knew if it was discovered somewhere.
So
in generality, who did it?
the earliest reference I saw in this line was maybe 80 something. Maybe it's actually the same paper you're mentioning.
What machine learning people call back propagation?
Yeah, back propagation, whatever that is.
I think it's just a consequence of the chain rule. That,
It is the chain rule, yes.
It is a consequence of
But who discovered first?
Yeah. No, well, I mean, it's a consequence. I'm just. I mean, let's use it for low bound, for example. I mean, this
Ah,
but,
I see.
You need, if you know this fact, then in order to get a low bound for a single output function, you can first prove a low bound for multiple output functions, like the gradient, and then use. But if you know if you know reference, where do people?
I only know one reference to the date of something like 89 or something, but I forgot what it is. I cited, yeah. Let's think of, yes. So, but in any case, like, let's forget about how to compute the Hessian, how to compute the gradient, and just working, maybe say first order oracle model. And let's worry about what's the minimal number of iterations we can achieve an epsilon error. So here is a quick overview of the result. That is, it's a 2x2 matrix, maybe like this. Either non-accelerated or accelerated. Either the function is not strongly convex or sigma strongly convex. Sigma strongly convex means here. So in this talk, I guess in the entire rest of the talk, I'm assuming the function to be smooth, meaning the Hessian is bounded. If it's not, there are some reductions, and which I don't want to talk about. It's notationally heavier. So then here is the convergence rate. So this one is like L over epsilon times x0. Let me first write them down. And the accelerated and here it is. Yeah. Oh, no, it's lock. Am I making sense? Yes. So basically, in the strongly convex world first, if we look at here, then what I'm writing here is the number of iterations before you can get an epsilon approximate minimizer to the function. So here you see that we pay a condition number times log 1 over epsilon, which is the same kind of kappa times log 1 over epsilon thing that showed up in the first half of the talk. And if we do acceleration, I'm going to define that in a moment, then one can get a first order method, meaning that we only make queries to the gradient and do something maybe fancier, we can get quadratically faster. This is when the function is strongly convex. If not, there is a similar thing happening here. Basically, if non-accelerated, we pay a convergence rate that's 1 over epsilon. And in optimization, people care about the so-called convergence rate because they don't really think about epsilon being constant. Actually, think about it. If you scale the function up by something, then epsilon, this is an additive epsilon. And therefore, like for optimization people, epsilon dependency is sometimes even more important than the dependency on the problem size for some reason. And they talk about this and call it an 1 over epsilon convergence, or sometimes 1 over t convergence if t is the number of iterations. And if you do acceleration, it can be quadratically faster. They say that this is 1 over square root epsilon convergence, or maybe they say it's 1 over t square convergence. T is proportional to 1 over epsilon, square root epsilon, and then epsilon is proportional to 1 over t squared. So that is basically what the best one can do in using first order method for convex smooth minimization if the dimension is high. So here I am assuming that, I'm saying that these two match the lower bound in this model if the dimension is high, meaning that the dimension I think is larger than, maybe t, well t is the number of iterations here, then it's tight.
So,
the reason is because
it's for the low bound.
for the lower bound, there is a similar thing if the dimension is large. In particular, think about it. If the dimension is 1, you can use binary search to find the optimal using a running time only log 1 over epsilon, independent of the condition number of the function. And more generally, one can use like, I think, ellipsoid method kind of things. Similar, essentially, it's the higher dimensional analog of binary search. But for this talk, I'm going to focus more on the, on the high.
If you're strongly convex, it doesn't depend on the diameter?
Oh, yeah, so that's a good question. So as we see, like, these two have like logarithmic dependency on the 1 over epsilon, and not really on the diameter of the. By the way, x0 is whatever point I start at the very beginning. If it's closer, it converges a bit faster. So actually, what sits here essentially